Hello and welcome to Module 2 of Mathematica for Physics. In this video, we will see the application of Mathematica to general relativity calculations. I will assume that you know a bit of general relativity. So let's write a code to calculate Christoffel connection. I have given the formula for the Christoffel connection for convenience, and in this formula, as you know, the repeated indices are summed over. So here in this expression, sigma is repeated. So this means we have to sum over the sigma. So we will calculate the connection for a given metric. Let's begin. So first, I define my dimensions as n. So n equal to 4. Then I define my coordinates. It's just a list which consists of spherical coordinates r, theta and phi, and time. Notice that my time is at the 4th position, not the 1st. It's just a convention. So now I give my metric. So the metric is the regular Schwarzschild spherical metric, which is given by, let me enter it first, 1 minus 2n by r, and this is to the power of minus 1, and then 0, 0, 0. Notice that I am entering a matrix. So a matrix is composed of 4 lists, 4 by 4. So the next would be 0, comma r square, comma 0, comma 0. The next one would be 0, comma 0, comma r square, sine theta square, comma 0. And the last one is simply 0, comma 0, comma 0, and the negative of first one, an inverse. So 1 minus 2 m by r. So this is our metric. So it will be convenient to see it in a matrix form. So I do metric and apply the matrix form operation. Remember, / means applying a given function. So this is our metric in the proper form we want. To find the inverse of a metric, or to say to find the inverse of any matrix, all you have to do is type the inverse function. So let me store it in a variable called inverse metric, and I simplify it and I give inverse of my metric. So this gave me the inverse. So I can also view it in the matrix form. And this is what it is. If it's really the inverse, metric product with inverse metric should give me 1, because A into A inverse is 1. That is identity matrix. So to check that, I metric dot inverse metric, and something went wrong. Oh, because we forgot to simplify it. So now we have the proper identity matrix. Okay. So now we can write our code to calculate the connection. Before that, I would like to remind you, if I want to address the first element, which is at the 1, 1 position, I write it as metric, square brackets, and then another square bracket, because if you remember, this is a list and this is a list within a list. So I have to include 2 square brackets, and I write 1, 1. So this gave me the RR component. Why RR? Because the first coordinate was r, so r component of the metric. Create some space, and now let me write the code to calculate the connection. Let me write it first and then I'll explain. So I will give the function Christ, and it takes three variables, a, b and c, and once the calculation is done, it defines, that is, it stores them as well, and the code is simplify. So in the formula, what is summed over? Sigma is summed over, so I have to have a summation. The summation would run from 1 to 4 because we are working in 4 dimensions, and I have r theta phi t, which is 4, and g with upper is the inverse metric and g with lower is my regular metric. So now this is simply, now I have to have a summation. You can have the sum symbol. You can go to palettes, go to basic math assistant. Here, if you go to the third tab and you see this sum, so I can have it here. Once I have it here, it gives me index, like what will run from where to where, and then the expression. So I define a d which begins from 1 and ends at 4, and now I have to enter my expression. So half was because there was a half here, and then I'll just write this whole thing. The derivatives with respect to mu I can enter as d, function of d. I'll show you. So first I have an inverse metric, and then I have d, derivative of the metric with respect to a given coordinate. Okay, since I have to write this again, let me just copy and paste it. And the last came with a minus. So this is CD. I'll close it in the bracket and then finally this bracket. Yes. So let me explain. First of all, I have the inverse metric. So inverse metric is just this quantity, g with upper index, and you saw the second quantity of it was summed over. So inverse metric AD, so D is being summed over. Now how do I write these? So this is the muth derivative of g sigma nu. Now mu comes from what we have written, from what the input we gave. So if my mu was r, so it will take an r derivative. If it was theta, so it will differentiate g with respect to theta, phi or t, whichever one we choose. We have specified the symbols in my quad list. So I differentiate the metric with respect to the quantity from the quad list. This is what this whole symbol means. So we have a differential plus a differential and then minus another one. So in all, we have this quantity over here, and then I've defined the whole connection as Christ function, where ABC refers to A is the upper index and BC are the lower indices. So let's run it and then let's calculate a sample one. Say if I want to calculate the RRR component. So I want to calculate RRR. So that would be 1, 1, 1, because if you remember, 1 referred to R. So when I calculate, oh, it's Christ. So I get the desired answer. Now you see there are 4 into 4 because lambda runs from 1 to 4, mu runs from 1 to 4, mu runs from 1 to 4. There are 4 into 4 into 4, 64 quantities. So I don't want to enter the function again and again. What I want to do is an automated function which just gives me a list of all the values, of all the non-zero values. So what I do is I create a table. So let me create it first, and then I'll explain the code. So I create a table. Now gamma, and I want it to be nicely displayed, so that's why I'm writing in the form of coordinates. So this basically means I'm printing out gamma ijk in the form of coordinates equals whatever the value is from the function. And let me close this bracket and the other one, and then let me define where do i's run from. I, j, k. Yep. Okay, so let me calculate. Okay, good. So what the issue is that in my connection, basically there are 64 quantities that we need to calculate, but it turns out that most of them are zeros, and I only want to display the ones that are non-zero, because those are the ones that are important to us. So what I've done is I've created a table. So a table works in the following way. When I write table, in the first argument, this whole thing is my first argument. It creates, here I write what needs to be put inside the table, and the rest arguments is the indices which will run from where to where. For example, since here I have ijk, so I will run from 1 to 4, j will run from 1 to 4, k will run from 1 to 4. So what I'm putting in is a condition that if it's non-zero, then store the value of the Christoffel connection from the function. So the condition is if is a simple condition, and what unsame q does is that if they are not same, it gives a true value, and if they are same, it gives a false value. So whenever it's not equal to 0, it gives a true value. So if of 1, that means it's passed and this whole thing is evaluated. If it's 0, then this whole thing is not evaluated, and at that position null is stored because it didn't have anything to put. So and when it is non-zero, what is being put, the toString function, it just enters the text version of this. So what I'm putting is gamma, the symbol, and the coordinate, this list and its position, I mean which element of this list depending on ijk, and then what is the value. So now when I run it, so you see it's created, it's a mess, but then you can see like there were lots of nulls around, and whenever there are non-zero values, and it has written them in a nice way. So now we only want the non-zero values to be listed nicely. So first of all, to do that, we need to get rid of all these extra brackets. I need to get it in a proper list form. It is a list right now, but it is a list inside a list inside a list. So it has two levels of list before the initial one. So to flatten it out, the function is called flatten. So flatten, and I pass b, and I need to flatten two levels. The reason I need to do that Okay, let me do it first. So you see now it became flattened, all the extra brackets got erased, and everything is in the first order. So the reason I need to do this, let me bring it up, yeah, is that when I want to show it in a column form, I should not have any additional brackets, because otherwise if I have additional brackets it will treat it as a matrix. So now I want to get rid of all the nulls. There is a very simple command which is known as delete cases. So I pass my list and I say remove wherever there's a null. So all the nulls are removed and I only have the elements that I need, all the non-zero elements. And to display them, there's a very simple command, table form, and I pass b. So here we have all non-zero Christoffel values with proper indices. Say so theta, theta r. So if you remember, Christoffel connection was symmetric in its lower indices, which means that the last two indices, it's symmetric under the exchange. So as you see, theta r theta and theta theta r are the same, which is what we needed. So this whole thing, after the script for calculation, what we wrote was just a decoration kind of a thing. We just wanted the output displayed in a nice way, but otherwise our code was done till here. So as we demonstrated, it would have taken this whole calculation hours to do on paper. With the power of Mathematica, we did it in couple of lines of code, and this was only possible because of the power of Mathematica in symbolic computation. In the same way, we can do Riemann tensor calculation. The formula for Riemann tensor is this, and again it's the same thing. First we calculate the connection and then we apply different derivatives. So in the same way, we can calculate any general relativity calculation involving tensors and other quantities. So in the next module, we will have a look at high energy physics calculations. Thank you for watching this one.